All right, we are nearing the end of chapter 21. We've just got a couple more sections to go. We're going to talk about optimization, which basically means finding the best solution to any given situation. And mathematically, that usually means finding the maximum or the minimum in a given situation. So you can see how it would fit in the chapter talking about the derivative. So let's go through some basic steps that you would have to go through to solve an optimization problem. The first thing you want to do, especially if you're a visual person, is you want to draw a large, clear diagram of the situation so you can see how all of the pieces fit together and how you could find the best situation. Then you're going to make a formula, and we're going to call that the subject. That formula is what you're actually trying to optimize, whether it's area or volume or something else. And it needs to be written in terms of only one variable, like x. All right? Right now, all we know how to do is find the derivative of an expression that only has one variable, like x. Okay? And we also want to write down any restrictions on x, because we may get some solutions that work for our equation, but they actually don't work for the real situation. And we'll see an example of that later. All right, and we are going to, once we have our equation, we're going to set the first derivative of that equation equal to 0 and solve for x. And we're either going to use a sign diagram or the second derivative to show that we have actually a maximum or a minimum. And we are going to compare that maximum and minimum to the endpoints to make sure that the maximum or minimum wasn't actually at the endpoints instead of at the place where the first derivative was equal to 0. All right, so those are our steps, and we're going to follow those steps in doing an example, and here's our example. We have a rectangular dish, and we're taking a piece of tin plate and we're cutting out the corners by a certain amount. So it was 25 by 40, so here's my 40, and down here is my 25. So I would label that on my picture, and then I'm going to cut a square out of each corner, and we're going to say that the dimensions of that square are x by x, because I don't know how big that square is going to be. And so I'm going to cut out all these corners, and I'm going to fold the thing up, and I'm going to make a box, and I want the box to have maximum volume. So whatever I'm trying to maximize, that's going to be my equation. And so since I'm maximizing volume, I need to find an equation that represents the volume of this box. All right? So if you look at the length of this box, well, we started out with 40, and then we cut x off of each side. So we actually cut off 2 x's. So my length is 40 minus 2x. My width was 25, but again, I cut x off of each side, so I cut off x twice. So my width is 25 minus 2x. And then when I fold the whole thing up, this x will also represent the height of the box. So that's going to be my height. So my volume will be 40 minus 2x times 25 minus 2x times x. And I know I'm going to take the derivative of this, so I better expand all of this out and get 4x cubed minus 130x squared plus 100x. And there is a restriction. Obviously, I've got to cut something off, so my x has to be bigger than 0. And since one of the sides is 12.5 or is 25, then I've got to cut something off that is less than half of that, which would be 12.5. So I can't cut anything 12.5 or more off of each corner. I don't know why I would even want to, but I need to write that as my restrictions just in case I get answers that are outside of this domain. All right, so here we go. Here is the function that I mentioned before, 4x cubed minus 130x squared plus 100x. If I take the derivative of that, I get 12x squared minus 260x plus 1000, and I'm going to set that equal to 0 and solve for x. Well, the first thing I notice is that all of those terms can be divided by 4. So I divide everything by 4, and that's what I get. And then I see if I can factor that, and I can. It becomes 3x minus 50 times x minus 5. And that is equal to 0 when x is either 50 over 3 or x equals 5. All right. Now remember, our domain went from 0 to 12.5, and 50 over 3 is well over 12.5. Okay, it's like 16 point something. So I can't use 50 over 3. So the only possible maximum I would have by taking the derivative is x equals 5. Alright, so what I'm going to do is I'm going to check for a maximum at x equals 5. And what I do, I've decided to do a sign diagram. I didn't actually show it, but what I do is I check what's going on with the derivative before I get to x equals 5, and sure enough, the derivative is greater than 0 there. So, for example, if I tried a number like 4, 3 times 4 minus 50 is negative, and 4 minus 5 is negative, so the whole thing is positive. So if the derivative is positive, that means that the original function must be increasing. Then I try a number that's bigger than 5, like 6. 3 times 6 minus 50 is still negative, but 6 minus 5 is now positive. So the first derivative is negative after x equals 5, which means that the original function is decreasing after x equals 5. So if I've got a function that is increasing before I get to x equals 5 and then decreasing after I leave, that's obviously a maximum there at x equals 5. Alright. Also check the endpoints of the domain just to make sure that the maximum didn't occur somewhere else. The endpoints were 0 and 12.5. But if I plug those in, I get a volume of 0. So the maximum isn't going to be occurring there. In fact, that would be the minimum. Alright, so I have a maximum that occurs at x equals 5. And to get the actual volume, which I won't do, but to get the actual volume, I would plug that back into the original function and figure out what the volume was. And that is an example of how to do an optimization problem. We'll do more of these tomorrow. But in the meantime, please feel free to ask me questions about the lesson itself or this example.